evening, brothers and sisters, lovely neighbors, citizens of this world. Good evening and welcome to one more live stream physics episode on this channel, Baji and Physics. As you can see, both Baji and some physics will be present on this live, and hopefully I see many of you joining very soon here who can confirm to me if you can see me and hear me okay. Baji is in the background tonight, giving us company during this physics lesson of tonight. We had a very engaging and nice and exciting live stream last night. So if you missed it, please do go to the live tab of this channel and check it out. It will be there posted under the live tab, and there will be some title of it, but pretty much you just go one back and look at it, okay? And you can scroll along and find many such episodes to watch and listen to, or just play in the background while you're doing other things, because we indeed have gone live a lot. I've been doing this for over a year now, and we have covered a lot of these different topics, especially and not limited to the realm of physics, astronomy, astrophysics, and cosmology. And of course, because I am the mother of Royal Bengal tiger cats, such as Baji, I also feature them on the videos because I cannot help myself. They are so very cute indeed, with the grace of God and the thanks to the universe. I am blessed. Thank you, universe, and evil eye remove. But of course, my children appear on these videos as well. And many of the videos are just solely on the kitty cats. So a number of cat lovers do enjoy this channel as well, and they do enjoy the lives as well, because generally they can find the kitty cats and see them, and we have engaging conversation. But also we hello Adam Dolson. Oh my gosh, hello Banks Ampha is saying hello. Hi, Banks. Adam Dolson is saying hi, Audrey. Just thought I'd check if you were streaming, and here you are. I am here, Adam. A tad late, but I'm here. I had my dinner. I took a nap earlier because I had to kind of wake up early for an appointment this morning at the doctor's. And so I had sort of a different kind of day, and I took a nap this evening, and here I am, hopefully refreshed for you guys. So I ate my dinner kind of late, had a phone call with a friend, all that stuff, and now I'm here. I am here. So generally what we do is we say hi to everybody that joins, and tonight I might even make some hot cocoa. See, I have some hot cocoa with me. It is called Swiss Miss, as in Swiss Miss. Milk chocolate flavor. So this is almost done, this hot cocoa, can of hot cocoa, and I will be making my last cup here tonight with you guys, and sipping it along with you, if that's all right. Acacio is saying, I enjoy the channel fully. Oh, thank you so much, my friend. Acacio, my friend, is here as well. Goodness gracious. These are some excellent supporters of this channel who have joined now. Adam is saying, did you just start? I think I got the transmission through the airwaves. You did. I just did start. I just started. Don't forget mini marshmallows. I don't currently have marshmallows in the house, but you know, I would love some. Old Guard is saying, Warum schreist du mich an? I don't know what that is, but thank you so much. And if that's German, please somebody translate that for me. Golden King is saying, how is your day? It's going. Luis Gomez is saying, hello, New York City. Hello, New York City. I am in Boston, but New York is not too far. Elijah is saying, good, keep up with chat now. It's okay to miss some messages as long as you're on the current messages. Oh, thank you so much, Elijah. I like to say hi to everyone as much as possible. Hot cocoa, so good. Yes. So let me share the live. I might do that thing again after a while where I title the live along with you guys. Warum schreist du mich an? I don't know indeed what that is, but it sounds good. Is that a good thing? Whatever that is. So I'm going to go get a mug. Please do, guys. Please do hang tight, because I'm just going to make this in the microwave. I just wanted to make sure I turned on the channel and started my live. She's so canceled now? What do you mean? What did I do? Did I say something bad? I didn't know. What is the meaning? That would be German. Hello, Kiyonosi. You guys tell me. What did I just say? The fans is leaked. Hello, I'm not a bot. Hello, Kiyonosi. Hello, Old Guard. Well, you guys should do some gifts and super chats if you're gonna make, if you're gonna give me such a hard time. I think someone's made me say something bad, but I didn't mean to. Snokomoi says buttercup. Hello, Snokomoi, how are you? Oh my goodness, thank you, Old Guard One. Old Guard One has sent some gifts. She's a Nazi. Who is a Nazi? Who? The clues are coming together. Thank you, Old Guard One. Was that something about the Nazis? Well, too bad and so sad. Thank you. Old Guard One sent marshmallow. I do need marshmallows. Did the marshmallows do an animation thing? Because that would be excellent. Hello, Wong. It was German for why are you yelling at me? Hello, Christy. Christy is saying, hello, I have a question. Osa shim'i buri desu ne ogenki desu ka. Hello, Kiyonosi. I don't know what you're saying, but thank you. Oh my gosh, of course, Mars. So let me say the top fans right now are Firefisher78 is number 1, Elijah is number 2, Adam Dolson is number 3, Christy Martin is number 4, Banks is number 5, number 6 is Kiyonosi, Wong is number 7. Thank you everyone so much for your support. I really appreciate it. Thank you so much. Thank you so very much. Oh my goodness. What is that? A poopy? Thank you for sending the happy poop. Thank you for the marshmallows. So, by the way, guys, so last night we were talking about some physics and we enjoyed the discussion very, very much. I really liked how engaged everybody was. Close, it means nice to meet you. How are you? Oh, very nice. Ozite is saying you sound like Snow White. Can I have a shout out to my YouTube channel? Hello, Christy Martin. Absolutely. Christy Martin is saying shout out the YouTube channel. There you go. X Powerhouse, X Power X House is saying hey Audrey. Hello X Power. Old Guard number 1 is sending gifts. Thank you so much. Appreciate you, my love. So let me see on the laptop if I can like these gifts and things like that. Also, let me share the live. I have forgotten to do all of the things because I got distracted. But I will say that last night we had a lot of fun. So if you missed that live, you should go check it out. And then definitely we had a number of very interesting conversations and we ended up talking about nova and supernova. And so I promised that I would cover that tonight as a topic and definitions of those things, nova, supernova. So I'm gonna do that tonight. So I have the page opened to nova. Hello, Deho Ags. Hello, Explorer. I got new physics jokes. Was that you who did the physics jokes last night? They were very funny. Hello, Vinny. How much for my cash or check? I'm not sure what that means, but you can send me money at my PayPal in the link in my description if you would like to support the channel. So we kind of know that when stars die, they have an explosion. We call that a supernova. And there's a few different types of supernova as well that we will get into tonight. But did you know that the first word, I believe, historically speaking, why did we call this thing supernova? There's a nova before the supernova that we came across. And so we will get into the definition and the history of finding the first nova tonight. So you might be knowing about supernova, but something that is less discussed is, of course, the nova, N-O-V-A, nova. And then we discovered even bigger cataclysmic events, because a nova is a cataclysmic event. There turns out there are even bigger ones, and those are called supernova. But these two things that I just mentioned, one is the nova, the other is the supernova, are two different things. So nova is actually when a normal star dumps some of its material onto a white dwarf. So this can happen when they are sort of in a binary, and I was mentioning this last night, where there could be different types of things that go on when a star dies, or in general with these different objects that are stellar remnants even. So I will be summarizing. So this is just a little bit of a preview for you guys before I share the live and continue on. So basically, I will be covering this topic tonight. What is a nova? What is a supernova? Certain classes of supernova. And I will be talking about nova in some detail, because that is something that we don't hear about too much. Talk about gravitons. We certainly can. Well, I would talk about gravitons more if I knew more about them. But since gravitons is not something I know much about, indeed, I don't know that they're discovered. And indeed, I don't know that quantum mechanics or particle physics has done a good enough job in describing gravitation. I think that is actually considered to be a flaw of these topics, that quantum mechanics does not have an explanation for gravitation. For gravitation, we go to general theory of relativity, which is all great, but these two theories don't really have a way to be unified. We've also talked about that a lot, how unifying these two parts of physics, one classical and one quantum, can be very tough, and people have tried and failed, including Einstein. Not limited to, but including Einstein, okay? So not that failure is what defines him or anyone, because indeed it could be sort of a tough and uphill task, could be very time consuming. People have tried, and the current status is that even if we have a candidate such theory, it's very difficult / impossible to test it out, for example, with superstring theory. So hello, says Ludite, is saying, long time viewer, first time chatter. What do you think about the rise of China? Hello, baby legs for life. When is the clapping with no hands gonna start? Hello, Zachary. Do you respect black holes? I do like black holes. EMS Chow Howl is saying, bruh, special relativity. Jesus loves you. Hello, Asher. Hello, Zachary. Hello, baby. Hello, old guard. Baby Legs is saying, how long have you been a trans king? Talk about graviton. So I was just responding to that. This is the first channel I've seen that's not religious, tarot reading, or bad gamers. It's nice, Lo. Thank you so much, Kyonosi. Thank you for acknowledging and appreciating. I really appreciate you. Ems Chow is saying, I'm a mechanical engineer. Tainted is saying quasars. We can talk about, so we have actually talked about quasars a lot as well. That is with an S, quasars. Justin is saying, do you like tacos? I do. Zachary is saying, does your mom know you're not in college right now? She does. I mean, she's probably asleep at this time, but she does know. How much for my cash or check? Says Vinny. What about Chevy Nova? I got new physics jokes. Okay, great. I think I've seen some of these comments already. Hopefully I've said hi to all of you. Please do like, share, and subscribe. Yes, indeed. Sorry about not saying that earlier. Hello, Zachary. Hello, Tainted Town. Hello, Marty. Why did the pirate go to Proxima Centauri? Q. Okay. Blue Waves is saying, marry me. Sorry for the typos. I got broken screen. Ems is saying, I subscribe. Thank you, Ems. Thank you so much for subscribing. Do you think the recent CME is affecting the Ring of Fire in the Pacific earthquakes? Latina or Desi, says Franklin. What do you think? What do you think of simulation theory? Nuggets, you're a winner. Hello, Zachary. Thank you, Ems, for the hearts. Desi, too smart. Aw, thank you so much. So, so basically we have been covering all of these topics, okay? So in case you're wondering, we have talked about quantum mechanics, we have talked about general theory of relativity, and we have talked about superstring theory. Not in a whole lot of mathematical details. We did talk a bit about general relativity mathematics at one point, but usually we try to keep it at a level of just the words describing things, and we take questions. Who are you? This channel is called Baji and Physics. Baji is a kitty cat who is right there. I am Baji's mother, and I talk about physics with you guys. And I also say hi to everyone. And you can put your comments in the chat, and you can show your love, and you can ask questions and things like that. I've been going on a fourth dimension documentary binge. Hello, Cindy. Hello, Indigo Dan D. Indigo Dan D. My wife is Goan. Okay, so she's from Goa. Okay, very nice. How nice. So, tonight we will talk about nova, supernova, and whatever else. But we do touch upon all these other topics that I just mentioned as well, in case you're wondering. And there's lots of these live episodes if you go to my channel's live tab. Indigo says, yes, that's me, Lil. You look just like Marcia. Hello, Tim Roos. I don't know who Marcia is, but do tell. So we have a lot of these live episodes done already in the past that has covered a number of these things, in case you're wondering. So sometimes it may seem like we're jumping in without any context, but I try to give you some context in each episode. But if you're wondering, we do have a lot more material already posted, and YouTube has them saved and posted for you. You look just like Marcia. Hello, Jumin. We are live. I will tell the channel, share. So I'm telling my channel in a post that we are live, and here we are. So I love to see all the comments coming in on all the chat messages. Please do keep them coming. Feel free to dominate the chat. It might be helpful to put a sign behind you saying like science channel or physics, etc. If quantum experiments could predict human choices, is it ethical to use that knowledge knowing it could undermine free will? That's a great question. Let me also go over here and do the live monitor. Do give me one moment because I want to make sure all the buttons are buttoning. Elijah says, I just joined. Did she say she's going to dominate everyone in the chat? I'm saying you should dominate the chat, as in send more chat messages. What is your physics background and credentials? Hello, Andrew. Hypernova Steve is saying hello. I feel like being with you would just automatically make me smarter. Hello, J Future One. Thank you so much. Thank you, everybody. So I did my PhD in particle astrophysics under physics. So my background is physics and physics. I have just the 3 degrees all in physics. But I also worked with astronomy department and hello Notorious, hello Jordan, hello Wong, hello Indigo, hello Ben, Tyson, hello. Tyson is saying I love you. Hello Tyson, thank you so much for all the support you showed last night. What are the physics on the massive, what are the physics on that massive forehead? Are you talking about my forehead? It is kind of big, isn't it? She is beautiful. Oh, thank you. As a woman, I'm over here struggling to finish one. What, a degree you mean? Well, I was also finishing one at one point, right? So it took me, I was in school for almost 10 years to finish those 3 degrees. And then I worked using my physics background for another 6 years. Well, 7, I think, at this point. So it didn't happen on day 1. At some point, I had 0 university degrees, right? And I was really hoping that somebody would give me a chance in their lab or something, because I came to the US to do research and to get more experience with research. Oh yes, you're gonna send me a poem. Hello Jed Clements. So I just have to make sure that I set up my chat or set up my live properly. So let me, what should I call this live, guys? Tyson is saying, good for you, I'm proud of you. Thank you, Tyson. So we thought yesterday that this is Neil deGrasse Tyson himself, because guess what? We're also reading from the book called Astrophysics for People in a Hurry by Neil deGrasse Tyson, of course. And I have 3 of his books with me right now. And actually, the Boston Public Library is asking for some of these books back. So Neil deGrasse, if you are here, you should just send me signed copies of your books. Thank you very much. Because it's kind of cold and I have to keep running to the library to get these books, among other books that I also check out. Not that I'm complaining, I'm happy to do it. But if you're seeing this at any point, you should certainly feel free to email me and send me your signed copies of your books. I mean, and you would not be the first author to do that. I also have this textbook that we're going to be using tonight, actually. It is called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. And so it is very nice when the authors just send you the book that you can study from, because these are all, well, I don't want to say expensive. The textbooks can be very expensive, but some of the other books are not. So I don't know. It would just be cool if you sent me a book, Neil deGrasse. What if it's Mike Tyson? Well, first I'd have to look up who that is. Hello, Greg Morales. Ben's TR. Hello, have a good night. Good night. Do you know these authors? Do you think AI will help us discover new physics? I thought that Mike Tyson is a bot. I mean, I figured he is in the sports domain, which I know very little about. But thank you for reminding me that he is a boxer. Buttered toast and cat, perpetual power, the buttered cat paradox. Okay. So what should we call this? Should we call this live buttered toast? I'm I'm just going to say physics with hot cocoa and Tyson. And study nova and supernova with me. How about that? Also, by the way, guys, please do like, share, and subscribe. I keep forgetting to say that. Indeed, please do like, share, and subscribe, because if you don't, then you might not find me again. And I would love for you to find me once again tomorrow night, the night after, all of the nights and all of the days. Please do like and share and subscribe, my dear friends. Thank you. Greg Morales is saying he has subscribed. Greg, thank you, Greg. Thank you, Tyson. Like, share, and subscribe, please. Very nice. I prefer the algorithm to lead the way. It is true. The algorithm does lead the way. So that's why I don't need a sign behind me or anything. Somehow the YouTube algorithm performs its magic. So AI, I don't know what else AI can do or not. I mean, it can do quite a bit, but I think AI has found you, this channel, and I have found you through AI. So there we go. Okay, physics with hot cocoa and Tyson. Study nova and supernova with me is what I'll say. Okay. Physics. We have also talked about definitions of astronomy, cosmology, astrophysics. Supernova. You will see in a second when I define when I submit the title of this live. I am editing it right now, live with you guys. So we're going to talk about that's such a funny comment. Freaky, freaky, freaky. Channel has no context and now science lady. Well, that's how we roll here. We don't give context before we spew a lot of facts. So, I even wore my red jacket for you guys tonight. So, we roll like a boss. Not you, your channel is normal. The universe is infinite, do you concur? Yes. Indeed I do, my darling. Arcturian Prince, the universe is infinite, do you concur? I do. Phoenix Squid is saying, genuinely need help, bro. It's nuts. What is? I'm talking about the train wrecked before you. Oh, okay. She's stacked. Stacked. Okay. I don't know what that means either. Their auto feeder is doing a thing. You're so beautiful, says Benny. Oh, thank you. I just had a Whataburger. Hello all day. Hello Arcturian. So, we if you're interested in cosmology specifically, we also have a lot of episodes on that, just so you know. Okay, we're quite diverse here. Join us for another. Thank you for the hearts and gifts and everything. Stand out. That's Tainted is saying, stand on that science business. 6-7. Facials. I'm interested in melons. Okay. Hello, Michael. Infinite can't be real because everything needs an end. Not necessarily. Hello, Benny. Oh, Tyson is studying optometry. I should know this. With math, wish me luck and say go. Are you Indiana? Are you in Indiana? I used to be in the Midwest. I don't know, Elijah. Somebody said to say 6 and 7. 6, 7, 6, 7. Argini is saying something. Hello, K-Dune. How old are you, says Greg. Let's see, who are the top fans right now? Number 1 is Old Guard. Thank you, Old Guard. Number 2 is Wong. Number 3 is Greg. Number 4 is Zachary. Number 5 is Benz. Number 6 is Elijah. Number 7 is Tainted Town Music. Number 8 is X Powerhouse. Number 9 is Jed Clements. And number 10 is Adam Dolson, my old friend on this channel. I'll do your poem tomorrow. Sorry, I was working today, and then I'll send it to you. All I hear is excuses, Jed Clements. Where is my poem? Number 7, yes. Join us for another physics live episode now. Da na 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 na. La 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 la. La 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 la. La 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 la. La 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 la. La 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 la. Cat Space Station? Yes, they do have a wall tree there, and last night we witnessed some zoomies as well. Okay, subscribe, channel. Do you have a theory on dark energy? Of course, yes. There is a, well, we have talked about dark energy, and it is something that we spend time thinking about and talking about. And dark energy is a current research topic that I'm always wanting to learn more about. So thank you for asking that. And we can certainly talk about the background and all that information about dark energy. Roses are red, some violets are purple. Sugar is sweet, and so is maple syrup. Hello, Michael. Hello, Steven. Steven! Hello, Notorious White King Kong. What's your talk on the after, or take on the afterlife? Full of light. Aww. Full of light. Indeed, my darlings. My darlings. I like your blazer. Oh, thank you so much. Okay, let us get into the topic of nova, okay? Enough chit-chat from me, at least. You guys, please continue your chit-chat, and feel free to say more stuff in the chat that has to do with this or something else. Go ahead, but of course I have mods, so you know, they might be more strict than me, actually. Are you my teacher? I am, my darling. I am. Joe Dirt is saying hearts. Well, thank you so much, darlings. Thank you so much. And Nusrat is saying hi, senora. Hello, senora, to you too, my darling. I have now been possessed by something else as well. Maybe it's from White. Okay. White holes. Yeah, indeed. I was wondering if I was visible. As soon as I pay my rent, I will send you a copy. Oh. Okay. Novae and supernovae. So the plural of nova is novae. Plural of supernova is supernovae. On the evening of 1572, November 11, Tycho Brahe was contemplating the night sky when he saw what he thought was a new star in the constellation Cassiopeia. So Cassiopeia spelling is Cassiopeiaa. Okay, and Tycho Brahe is this famous astronomer, especially known for his observations and work with observing a lot of objects in the sky and keeping very good notes about them. So a very very good. Somebody put Cassiopeia in the comments. It's actually Casssiopeia. Okay, interesting spelling there. So basically, Tycho Brahe, you might hear, if you ever taken any astronomy or even physics, you will hear about this guy. He did a lot of groundbreaking work, especially in observation in astronomy. We learned a lot from the notes he took of the night sky, the detailed measurements and observations that he did back in the day, 1572, so long ago, and kind of like before modern times and modern astronomy, but he was doing this work. And he took note of this and he thought it's a new star. Now, this guy looks up at the night sky a lot and he keeps really detailed and good notes on the night sky and, where the objects are, if they've shifted, all these things. So he would be the perfect guy to find out if there is a new star, right? Why I do this? Because turns out it's not maybe a new star, but this is how it was found. Ultimately, astronomy is an observational science, a very, very observational science. It is one of the oldest sciences, and it literally happened with just people looking up at the night sky when it got dark, right? People had time, they weren't looking at their phones as much because maybe they didn't have phones, and they had time and they had, just imagine if the sky was just full of these stars, or sources of light, really, bright objects. Could be stars, could be something else, right? Could be galaxies is what I would say, or binaries, don't want to get sidetracked there. But pretty much people can look up at the night sky and use that visible light, the light that enters our eyeballs, and the one that we can process and our brain can process is visible light. It's the visible light spectrum, the wavelength of light that we can see and process. And people were using that traditionally to do astronomy. Now, of course, cut to now, in modern times, we do astronomy with other wavelengths of light. We do astronomy with particles that are not even light. We do astronomy with other means. But back in the day, the traditional way was this. Nusrat is saying, I want to take you for Nobel Prize. Hello, Pranay. Hello, everybody. So this is a prime, this sentence right here is a prime example of how old astronomy is, so I'm happy about that. So again, on the evening of 1572, November 11, Tycho Brahe sees what he thinks is a new star, okay, in this constellation Cassiopeia. Because back in the day, those constellations really help people to also keep track of what they're seeing, and if things have shifted, if the constellation, something changed, like he would know because he looks at it all the time and he keeps such good notes, which, by the way, is an extremely important process in science, is data collection, data storage, data management, right? We do this, this is even more bigger topic now because we have ability to collect a lot of data, and so much so we can even do AI with the data. But guess what? Like, this is what Tycho Brahe was doing back in the day, is collecting data, and it's extremely important, if not the most important thing in any kind of experimental or observational science, which astronomy is. So since this was a blow to the Aristotelian dogma that no new stars can appear in the heavens. So remember, back in those days, because of religion and old-fashioned beliefs like that, and people kind of really valuing the heavens as something that had a spiritual significance, something that was of religious value. And the heavens, there was earthly things and then there were heavenly things. Even the moon was heavenly, right? Or the sun, or some constellation in the sky that you see all the time. Something changing in the heavens was not a good thing, because it was considered that the heavens were perfect, like the heavenly objects should not have any change. So actually, whenever people challenged that was a really difficult thing. It took a lot of courage to say that something in the heavens could have any change, because the heavens were supposed to be perfect, and the heavens was pretty much anything that wasn't the earth, right? So action, and this is an important note to think about, because of course the very thing that those people were saying at that time, or what they wanted to hold dear about the heavens not changing, is what will continue to challenge that theory, because we do see that the heavens do change. Okay, so this Aristotelian dogma was that no new stars are really allowed to appear in the heavens because heavens are perfect. Tycho rushed into printing this new work, the Nova Stella. So he called this the Nova Stella, which is the new star. So this nova comes from that new word, Nova Stella. Following the lead of Tycho, astronomers applied the term nova to unresolved celestial objects whose flux increases by a large amount over a short period of time, giving the impression of a new star appearing in the sky. So, now we have defined out what we mean by a star and things like that. Back in the day, when you're doing this type of astronomy with visible light, really the more specific would be just why, like the way I was saying it earlier, when we say, oh, look at this night sky and it's full of stars. So I want to clarify, like, first of all, it's really what we see is objects. Okay, if you say objects, then it will be a bit more general, and then we can get into the details of what that means. Objects could be stars, it could be galaxies, it could be binaries, right? It could be a black hole, but you're seeing what's around the black hole, not really the black hole, because the black hole is going to be pretty dark, but maybe around it, So those types of things, right? So it pretty much back then, Nova Stella, as in everything was just called a star, right? They didn't have the ability to resolve better, to see sometimes that actually a star is really a galaxy, a whole galaxy, right? When we look up at the night sky, even now, if you just look in any direction, a lot of the times, what you're seeing is actually a whole galaxy. It's not a singular star. Or what you're seeing is a binary system of stars, right? At least a binary. So oftentimes these things are actually in binaries. So so he called this a new star. But what was it really? So this is how the nova was first discovered. We want to give credit to Tycho Brahe because he did this observation. So whoever first discovers an object, even if they get it wrong, we still want to give credit to that person because they discovered it, they noted it was there, they noted the differences, and that they took down the notes, they literally wrote it down and marked its position in relative to other things. So this whole process of the data taking is extremely important. If we don't have this, and also if we don't record this properly as a data collection and data recording process, then you're basically completely you just don't even have that, right? So that's a very, very, very important step in science. So always be taking notes, always keep your lab notebook, and always write down what you see, because others may or may not see it, and even if they see it, they may or may not write it, because he called it Nova Stella. He thought it was a new star. Turns out it's something else, but he's the one who found it. Okay, so sometimes science takes a number of steps to get to where you are now, but the process is still very important. Hello, Nusrat. Thank you for the lovely comment. So Tycho rushed into printing with this. So this is another thing that I find funny, because it's so much in the DNA of a scientist to print and publish when they have found something new, right? And people should not, you could be wrong. The thing is, like, when you rush to print something, when you rush to publish something, you could be wrong. So, but at the same time, that is part of scientific process. Part of scientific process is to publish. You could be wrong, but just try to be as correct as you can. Just try to give all the details and accurate precise everything that you can. Just do your best in that publication so that it's still useful for the next steps of scientific process, because that first part is so important. Okay. Uh, hello, Cupid. How are you doing? Hello, Notorious. So he rushed into printing this. Following the lead of Tycho, astronomers applied the term nova to these types of unresolved celestial objects whose flux increases by a large amount. So by the way, another thing is that sometimes when an object is, say, in the sky, right? Like certain objects, they don't have a lot of change in flux. Like a lot of stars may not show a lot of change in the flux, as in the flux of light that we are getting from the star. And back then it would probably just be visible light. But pretty much, if the flux is not changing a lot, then that's one type of star. If the flux of the object, which we think is a star, changes a lot, then that's another type of star. This is where the flux had changed a large amount over a short period of time, giving the impression of a new star appearing in the sky. Hello, Edgar. Edgar is saying, ¿Cómo estás? Yes, you can ask a question. So yes, flux is related to luminosity. Somebody's asking. So luminosity is basically a power. It's a total power output, whereas flux is when you, it's something like when you take the luminosity and you divide by the surface area of a, like it's sort of an approximation, really, because no object is exactly going to be a sphere, but basically it's luminosity divided by the surface area of a sphere with a radius equal to the distance from that object. So basically flux is kind of like luminosity divided by an area. So the units of luminosity, I believe, and you should double check, would be power, like watts, for example, right? Power is like energy per time. So power would be an energy divided by time. So like joules is energy. Power would be watts, like, you know, like your power bill might be in watts or megawatts or something, right? Luminosity will be sort of like a power that we're getting from a star, for example. But then sometimes it's useful to, you know, for reasons of keeping the logistics and doing all of this work, it's useful to put it in terms of flux, which is that power divided by an area. Hello, Nusrat. Thank you so much for your kind comments. That's very kind of you. Nusrat is saying, I envy your strong will. You're not embarrassed by comments and maintain your presence of mind and a pleasant expression on your face. Well, thank you so much. I have a lot of practice. And you can too if you want to start your own YouTube channel or Instagram or Facebook. In fact, you should add me on Instagram. Cupid, thank you. Marty, thank you. I don't know English well and I can't understand your words, but your eyes keep me glued to the screen. I just look at them and I'm touched. Oh, I appreciate it, Nusrat. Hello, Joe. Hello, Dakota. Yes! Oh my gosh! Flux is also the word for soldering. There in the, when you solder, I did have to solder too in grad school. So when you solder something, the little bit of little liquidy thing that you add, in the solder is also called flux. But this flux that we're talking about here has to do with power divided by an area, okay? Anyone have any physics pickup lines? Hello, Dakota, HVAC Tech. Oh, very nice. I thought we couldn't see other galaxies with the bare eye. Well, we wouldn't be able to resolve them, but actually, yeah, no, you can. So we can see. A lot of the objects that you're seeing are actually galaxies. Hello, Diamond. Hello, TWC. How are you doing? We are doing a Kitty Cat and Physics Live. Feel free to like, share, subscribe. You should definitely come back and give us some hearts. Don't leave without sending your love first. Okay? Okay. Okay, so you seem unsure about what you're saying. Hello, Jimmy. कोई इतना खूबसूरत कैसे हो सकता है? Okay, I wanted to look at the comments and the chat messages really quickly. Hello, Jebin. Goodness gracious, thank you so much, everybody. Can we get 55 likes? We will keep on going. I like in Einstein's gravitation is not responsible for people falling in love. If astronomy were a person, it would marry you. Well, thank you so much. Okay, so when a nova produces an outburst of light, its luminosity can briefly increase by a very large factor. So whatever luminosity we were seeing for that object, it increases a lot, okay, for a brief period of time. For example, consider the nova. So now we have a nova name, as in we have a nova that we can consider as an example here. And it is called V1500 Cygni. So you can look this up yourself as well. So this is V1500 Cygni. It was an inconspicuous object with about a luminosity number of 20. We haven't really defined those things yet, but just take the 20. At the peak of its outburst, it had that same number was around 2, making it the second brightest source in Cygnus after the star Deneb. So I guess this thing goes down with the luminosity increasing. At maximum, therefore, the flux of V1500 Cygni had increased by a factor of 2 times 10 to the 6. So the flux number might be more helpful to understand. So basically, the increase factor of the flux from this Cygni was 2 times 10 to the 6. So almost a million, or more than a million times more flux is coming from this object. Okay, the sharp rise to maximum flux was followed by a gradual decline over the course of months. So this nova situation, we still haven't gone into the details of exactly what the thing is doing, but whatever it is, its flux is increasing to this big number, much bigger than the original flux, and then it gradually declines again over the course of months. So this is a transitionary kind of thing. It's not like an event, or it's not like an object, like a star that's pretty stable. It's doing something, and we will see what that is. And it's sort of what we would call a an event, sort of a transitionary event. Okay. Yeah. Okay. So because even a supernova, I would consider that an event. The star is the object. When it's dying and supernovaing, that's an event. Same thing with this. Okay. So the modern definition of nova states that a nova is a type of cataclysmic variable as opposed to a pulsating variable like a Cepheid. So I'm sure even the people who were trying to sort of put it in a box or define exactly what it is, they probably thought about this a lot. It's not like they're like, oh yeah, that thing, it's this. Sometimes you do have to think about things a bit more and learn more. So for example, the naming of it has stuck, new star or nova stella, but actually we will see now it's not really a new star in that sense, right? So this is where basically a normal star is dumping gas onto a white dwarf. So now backing up a little bit, we mentioned this already last night and a number of other lives, but basically when a star dies, when it has run out of its nuclear power, because to be a star, of course, you need to have a nuclear reactor in your belly and be making heavier elements out of the lighter elements. And that's actually how we're all here. All the elements heavier than hydrogen and helium are made in stars, etc., etc. So a star is a star when it's burning, when it still has that nuclear power going. But the other thing that a star has is a bunch of gravitation, because a star is very massive. So when it runs out of nuclear power, it will collapse onto itself under its own gravitation. So gravitation wins when it dies, okay? So a star dying is basically gravitation winning. So then what ends up happening, and we will talk about supernova in a bit as well, but somehow we needed to talk about this in order to define a nova, which is funny, is that basically you can have this big cataclysmic event, an explosion, etc., lots of things going on. But then what you're left with at the end of that supernova is a stellar remnant, or what we call sort of the dead body of a star. What's sort of left after the explosion's done and everything's been, not everything, but a lot of material has been spewed into the interstellar spaces around the star. And you're left with just the stellar remnant. And depending on the mass of the original star, you will either make a white dwarf, a neutron star, or a black hole. So the most massive stars make black holes when they die. The medium massive stars, but still very massive, would make neutron stars, which are, by the way, pulsars. Somebody has mentioned about pulsars. And then the least massive stars, or the low mass stars, like our sun, for example, would make a white dwarf. These are the three different categories of stellar remnants. White dwarf is one, neutron star is one, and these are just names, okay? Neutron star is not a star, it's a dead body of a star. So white dwarf, neutron star, and black hole. Those are the three options for stars. Pretty much in the fate of a star, one of those three is written, okay? So now, what a nova is pretty much a normal star. It might be in a binary with a white dwarf, and it has decided to put some of its own material onto the white dwarf. So it's dumping some material onto the white dwarf. So like a gravitational interaction is going on. It's kind of like a couple. Sometimes stars can be in a binary. Sometimes other objects, like even a dead star, or like one of the stellar remnant types, like say a neutron star, can be in a binary with another neutron star, or Oh my gosh. So, or a neutron star can be in a binary with a black hole, or a black hole can be in a binary with another black hole, and things like that. So now imagine if sort of a star that's not dead yet, right? It's still a star, is in a binary with another object, which happens to be, in this case, a white dwarf. And because of their gravitational interaction, their dance that they're having between them, the two are maybe revolving around each other. One, that is the normal star, starts to put some of its material onto the white dwarf. Okay, so thus a nova is actually a closed binary system in which a star and a white dwarf orbit their mutual center of mass. So we also know that when two massive objects like this revolve around each other, they're actually releasing gravitational energy. We actually have picked up on such gravitational energy. We have measured gravitational waves, for example, from such a thing, like such a binary system, for example, now in modern astronomy, in the last less than a decade, actually, which is really exciting. And so we know that this process releases gravitational energy, which means that it kind of that system is losing some energy, and it's getting closer and closer together. Okay, so literally, if a binary system had two objects that are kind of farther apart, over time they will actually get closer together and keep on orbiting each other, and ultimately could be merging. Okay, and of course, if they merge, that would be another cataclysmic event. But even this pre-merge dance can still release energy and can still show up in various different waves, such as in this nova way. Okay, so tossing, or the nova is actually a closed binary system in which a star and a white dwarf orbit their mutual center of mass. Tossing material onto a compact object such as a white dwarf or a neutron star is an excellent way to convert gravitational potential energy into thermal energy. So once again, the two things that are orbiting each other are releasing gravitational potential energy, and part of it, so part of that we could maybe catch here on Earth with something like LIGO, and pick up on that gravitational waves. And part of it is basically converting some of that into thermal energy, because this thing has now gone onto the white dwarf, right? And boy, will that do something, which we will now read about. So we still need to explain why pouring gas onto a white dwarf produces sudden cataclysmic outbursts of light rather than a steady glow. So it, far away, this thing is happening, but far away, this sort of thing is happening. But we can ask, well, what's the big deal? If we dump material onto a white dwarf, what happens, right? A white dwarf is not a normal everyday object. I mean, maybe it's pretty normal at this point, but it is also something kind of special. So white dwarf, remember, is a stellar remnant, and a white dwarf is a stellar remnant for low mass stars that have died, which is kept stable by electron degeneracy pressure. As in, why did a white dwarf not collapse farther, as in become even more compact, collapse under gravitation even more? Why? Because of electron degeneracy pressure. So there is a certain environment on a white dwarf. I mean, it is kind of different, okay, than a normal star, for example. So we have to think like, okay, this normal star is putting some extra material on the white dwarf, but what's the big deal? Why is there a cataclysmic event happening with the luminosity going up so much and then gradually declining over months. Because honestly, that is the same sort of thing, but even more. What happens in sort of a supernova, like the signature of a supernova, is also something like that, where there's a lot of luminosity, a lot of flux from an object because the star has exploded, it's dying, right? And then it kind of goes down. The flux will decline over days and weeks and months, okay? And again, I'm skipping over details because we also can ask flux of what, right? Could be light, could be other particles, things like that. Hello, Janice. Hello, Young. Hello, Orville. Yes, our sun will one day become a white dwarf. This is astronomy, a bit different from astrology, but thank you, Young. Hello, Rahul. Hello, Joe. So a white dwarf is already a stellar remnant. If you disturb a white dwarf like what this other star is doing, we will see what happens, and basically you get this nova situation, which is kind of different from a supernova. A supernova is just a star dying. This is some interesting interaction between a binary of objects that is leading to what we call the nova. Don't pour gas. Exactly. Thank you, Nusrat. Pakistan. Somebody asked. Southwestern Asian Indian woman. Southwestern? What is Southwestern Asian Indian woman? I think India is considered Southeast Asia. Is that not right? Hello, Kumar Patel. Hello, Agar. Okay, we will now keep on going. South Asia. Hello, Cat Staffer. How are you doing? Can we let her talk without trying to date her? Oh my goodness. You need a mod. I mean, I do have a couple of mods, but it's okay. Let them do their thing. I do need the engagement. Someday all stars will run out of fuel. Well, we're also making new stars. There are very enriched spaces as well that are sort of birthplaces of new stars. So a star dying is not the end of the universe, quite literally. We come from a dead star as well. If stars didn't die and spew their material into space and make gas nebulae, we would not be here. We come from also a gas nebula, a very good one. Thank you, Cat Staffer. Thank you for being here. Please do like, share, and subscribe. I need it. John, hello. Jayanez, hello. What part of India are you from? Spew. Yes. Okay. So, all right. So, can you guys do some gifts? It's gotten a little cold in the chat. So let's see. We still need to explain why pouring gas onto a white dwarf produces this cataclysmic kind of event and not just like a chill, steady glow. that we would see. We don't see a chill, steady glow happening. We see something cataclysmic. Let's look at what happens when a star expands past its Roche limit and pours gaseous hydrogen onto its close companion, a white dwarf. Thank you, Joe. Thank you so much. I'll come back to your comment. So, Roche limit. So this is something to do with that gravitational release of energy that I was talking about, where the two objects in a binary is coming closer and closer together over time, losing gravitational potential energy. And at some point, one of the objects is really getting into the space of the other and putting stuff on to that object. So that's what's basically this going past the Roche limit, and pours gaseous hydrogen onto its close companion, a white dwarf. So this companion is no longer a companion, it is a close companion. The outer layers of a star are actually a mix of hydrogen and helium with a smattering of heavier elements. So we know that stars have a nuclear reactor in their belly. So depending on which star and depending on how big and what it has made, for example, a lot of really massive stars may have an iron core, right? It takes some work to make something like iron, for example. And like for example, our sun is not making iron, right? It's making just helium from hydrogen. It's a low mass and young star. So not every star is going to be the same and doing the same things, but pretty much I'm just giving you an idea that the nuclear reactor is in the belly, and you would find the heavier elements probably closer to that. The outer layers is going to be gas. It's going to be mainly hydrogen and helium, which, by the way, quiz question, hydrogen is still the most abundant element in this universe. Not on Earth, not talking about the Earth, but in the universe, hydrogen is the most abundant element. We all came from that, right? Hydrogen and helium. So if you had to answer the question, like pretty much, if it's dumping stuff, what is that stuff? It's going to be hydrogen, helium, just like take it for granted, because that's the outer layers of the star. And some heavier elements, like some heavier elements will be in the mix of things, but mainly those things. So for simplicity though, let's just assume that it's pure hydrogen. I mean, most of the universe is pure hydrogen anyway, right? So we can do a little bit of math now, considering that it's just pure hydrogen. Joe is asking, what do astronomers do most of the time at work? I mean, they can, if they're observational astronomers, they can go out and observe if the night sky is, good. Like if the moon is not full. Best would be if there were no moon and they can see the night sky. They can set up instruments. There's a lot of instruments, and they can go and observe whichever part of the sky that they're interested in. Often they have an object that they're following. Things like that. Sometimes they work on instrumentation, like making the technology better to make those measurements. And sometimes they're analyzing data that's been taken already, for example, say by Hubble. Hubble Space Telescope has given us a lot of data. So a lot of astronomers just look for, wait on, I mean, at least they used to. I'm not sure if Hubble is still doing this right now, but basically they would wait for Hubble time. They would have Hubble look at a part of the sky that they're interested in, and then collect the data there and analyze the data there. Okay, so things like that. So those are some things that astronomers do. So if we assumed that the stuff that it's dumping onto the white dwarf is purely hydrogen, well, the surface gravity of the white dwarf is high. The hydrogen is flattened into a layer with a short scale height. So we're going to do a little bit of math now, okay? This height is given by kT over small g mu mp. As hydrogen is poured on, as long as the atmospheric temperature T, which is the T that I just mentioned, is roughly constant, the scale height H remains the same. Thus, as more and more hydrogen is poured into a layer of constant scale height, the density as the base increases steadily until it reaches the point where the electrons become degenerate. So now we know that white dwarf is held stable by electron degeneracy pressure anyways, right? That is how a white dwarf is white dwarfing, because a white dwarf is a compact object which did not become further compacted because of electron degeneracy pressure. The gravitational collapse is not strong enough for a low mass star to go all the way to even more dramatic compacting or even more dramatic collapse, which would lead to, say, for example, a neutron star or a black hole. So white dwarf is held in place by its electron degeneracy pressure. Now you're adding some more stuff onto it, okay? So when the density is sufficiently high, or sorry, so electrons are degenerate, we know that. As the hydrogen relentlessly continues to pile on, so literally, relentlessly, this one star is piling on. So by the way, if you guys wondering, are ever wondering what is piling on mean, this is what it means. So you're literally piling on to your close companion. Sometimes this happens in couples too, I imagine. I'm single, so I wouldn't know too well. I mean, not right now anyways. I used to be not single, but this can happen in couples where one person is piling on to the other tremendously, just awful, right? I mean, this white dwarf was minding its own business and suddenly you're piling on, and it can be relentless, okay? So you're adding to this electron degeneracy. As the hydrogen relentlessly continues to pile on, the pressure and density at the base of the degenerate hydrogen layer must continue to increase to maintain hydrostatic equilibrium. When the density is sufficiently high, fusion of hydrogen to helium. So now it's not just hydrogen. You're adding this material, it's hot. You can start to have fusion of hydrogen to helium via the proton-proton chain. So we can talk about that. It's a PP, it's a nuclear reaction, PP chain. We can talk about that, but that starts to happen because you're converting, remember, where is this energy coming from? You're converting gravitational potential energy to thermal energy, right? This piling on is happening and it's hot. So piling on plus hot means there could be a nuclear reaction happening where now the hydrogen is like, oh boy, I will now make helium, which is crazy because that's a nuclear fusion reaction, right? So that could be very problematic indeed. It's not problematic if you're okay with that, but when the density is sufficiently high, fusion of hydrogen to helium begins with a hydrogen flash. So now you've fused hydrogen to make helium, analogous to the helium flash with which solar mass stars begin helium fusion. So by the way, this PP chain type of stuff is important because a lot of what our sun does is kind of something like this, okay? So this is common stuff. This is not like the other thing is that making helium is one of the sort of easier nuclear reactions, right? Like it's not that heavy of an element. Even the Big Bang gave us a bit of helium. So even the Big Bang conditions gave us a bit of helium because the Big Bang nucleosynthesis just gave us hydrogen and helium mainly, right? That was it. So it's not like, I mean, nuclear reactions are hard, like you need a lot of energy to do them, but making helium is like one of the low energy ones, right? So at this point, because of all the piling on, the thing is making helium. The material on the white dwarf's surface becomes, in effect, a hydrogen fusion bomb. So this is something you might be able to relate to if you're into like that sort of stuff, like defense, weapons, and things like that. Hydrogen bomb is basically the same thing, hydrogen fusion, right? So that's what's happening. So this is what can happen when your partner piles on too much. You basically make a hydrogen freaking bomb on your partner, which is bad. A bright nova is observed to release as much as 10 to the 38 joules of energy. So now what does that white dwarf come hydrogen bomb situation do? It will release energy now, right? The energy has to go somewhere. There's a cataclysmic event, like a full white dwarf surface bomb, you know? So that will release a lot of flux. And that's why we saw that big rise in flux and then the gradual decline. The energy released by fusing hydrogen to helium. So this is, just making hydrogen to helium. I mean, that's how we are here. We get light heat energy from the sun. also making hydrogen to helium. So it is around 6.4 times 10 to the 14 joules per kilogram. So it depends also how much mass there is to do this anyways, right? So that's why we now want to say how much energy per how much mass. Thus, a bright nova requires a mass of hydrogen equal to 10 to the 23 kilograms. Lots of hydrogen. This is roughly, so 10 to the 23 kilograms is not that bad. It's just roughly the mass of the moon, actually, to give a comparison. The energy released by the fusion of degenerate hydrogen. By the way, guys, I really appreciate all your emojis, gifts, all that stuff. Appreciate your support. So the energy released by the fusion of degenerate hydrogen is sufficient to blow the outer layers of non-degenerate hydrogen into space. So partly it's also that degeneracy keeps things kind of stable, and whatever is not degenerate is the one that's gonna get blown out. So the nova GK per C, so this is another one, for instance, had a major outburst in 1901 February. A century later, it was surrounded by an expanding gaseous nebula. So this is so interesting. It's almost like we can see something like this happening in a sort of real-time manner, because I mean, things in astronomy can take a long time, but if it's only about 100 years or so, there could be something that we are able to see for some finite amount of time, right? So since the white dwarf itself is unharmed by the nova explosion, novae tend to be recurrent phenomena. The more energetic, so it's almost like you're piling onto the partner and then something happens, you know, we see this big flux, and then the partner is fine again, and then they're in a toxic cycle, in other words, okay? So once again, the white dwarf itself is unharmed by the nova explosion because the explosion releases things that are those non-degenerate things, and so whatever's going off, there is still the compact white dwarf at the end of the day. So anyways, novae tend to be recurrent phenomena. The more energetic the outburst, the longer the time until the next outburst. Dwarf novae have an interval between outbursts of 3 weeks to 2 years. Recurrent novae have an outburst of every few decades. Bright novae like V1500 Cygni are probably recurrent phenomena as well, with outbursts every 1,000 to million years. So depending on exactly the nova situation, you can have different time intervals. So depends on the couple, right? Exactly how often you see the explosion type of thing happening. Novae are energetic events. The brightest nova outburst can produce as much light in a week as the sun does in 10,000 years. So this is why we call it sort of this like cataclysmic, big luminosity event. It catches our eye, and it's a transient event. It's not like it's going to be that luminous all the time. Hello, Spearhead. Yes, my background is particle astro. Particle astrophysics is what I yes, indeed. Thank you for the super chats and gifts, guys. Thank you indeed for the super chats and gifts. Can I tag the book? The book is Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. It's something we use quite often on the channel, actually. It's a textbook for astronomy majors. Thank you, everybody who please do like, share, subscribe. Please do like and share and subscribe. Hello, Benny. Hello, Mark. Hello, Wet Dream. Thank you, Matt. What is your thesis? You want to know what my thesis is called? Okay. I wanted to become astrophysicist, ended up with aerospace engineering. Michael is saying don't laugh. Let's talk blue super. Oh my goodness. Like and subscribe. Is tarot cards so common that people are asking me if I do tarot readings? Thank you, Cat Staffer. Appreciate you, my darling. Benny, it's gonna be okay. What's your vibe? Says Bing Bong. Hello, Bing Bong. It's gonna be okay, guys. It's gonna be okay. It's gonna be okay. So somebody asked me my thesis title, and I kind of forget exactly what I called it. It was a while ago. But it's something like Studies in Particle Astrophysics, and you can Google it if you'd like. Thank you, Gabe. Her vibe resonates at the frequency of hydrogen. Aw. Hello, Bradley. If I can read tarot, I mean, I could give it a try. I do believe in spiritual stuff. It's just water. Okay, let's finish up novae. Novae are energetic events. The brightest nova outburst can produce as much light in a week as the sun does in 10,000 years. So it's a lot of light. However, novae pale in comparison to supernovae. So there is novae that we just talked about. It is when a couple of binary objects are losing gravitational potential energy, converting some of that to thermal energy. One partner is piling on, quite literally, to its close partner. So a normal star could be piling on to a white dwarf, and because of basically that leading to an extreme situation of then that becoming a hydrogen bomb-like situation, fusing the hydrogen to helium, because it's a lot of piling on happening in that hot temperature as well. Then it can blow off some steam. You know, some of that energy goes out, and then the white dwarf just kind of continues to do its thing. And so every now and then this can happen, and so a nova is sort of a recurrent kind of situation, unlike a supernova. Okay, we will get into the supernova in just a bit here. Supernova is different. there's not really a recurrent thing happening with a supernova. It's the death of a star. It's quite permanent. You will also see a lot of flux happening with a supernova, and then you will see a gradual decline. And it's not like you would see it again and again happening like we would with a nova. Okay? Whew, it's kind of cold. I guess Baji has gone upstairs. So, okay, the novae will pale in comparison with a supernova because supernovae will be even more energetic, okay? So, supernovae have absolute magnitudes that are at least 7 magnitudes brighter than the brightest novae. The term supernova, the hyphen has since vanished. We just say supernova without the hyphen, was first proposed by Fritz Zwicky and Walter Baji in 1934, when they suggested that outbursts of light, much brighter than ordinary novae. So it's kind of funny that first we discovered nova all the way back in 1572, right? I believe was the year, by Tycho Brahe, and he called it a new star, nova stella, and we get nova from there. And then now we have this other thing, other event or a transient event called the supernova, and because the naming comes from basically a nova that's much, much brighter, but really a nova is kind of a different process than a supernova, okay? Sometimes in these older sciences like astronomy, you would get certain naming that kind of lasts for a long time, but the naming might not always be super logical or related, okay? So the term supernova, you know, 1934 comes from the much, much brighter nova thing, would be produced when the core of a massive star collapsed to form a neutron star. So now there are other types of supernovae. Let's just see some of them here. But pretty much probably when they were first finding, so also remember that sometimes in astronomy when we discover something, it might be sort of the extreme version of something that we have discovered first, and then we keep looking and looking, and we might discover other variations, and so on and so forth. So when they first saw a supernova and you know started to kind of track it, it was this type of supernova. That is not to say that that isn't the only type of supernova, okay? Okay, so astronomers, once they acknowledged the existence... Thank you, Spearhead. I do appreciate your super chats very, very much. Have you heard of PISN supernova? I don't think I have. It is a class meeting. Okay. Astronomers, once they acknowledged the existence of these extraordinarily luminous supernovae, classified them according to their spectra. So another thing that astronomers tend to do a lot is the way in which things are measured, the way in which things are observed. You know, spectra plays a huge role, could be sort of a way in which those things get categorized or classified, okay? So simply enough, they distinguish between type 1 and type 2 supernovae. So there's only a couple of types, but then there's a sort of a subtype. But basically, there's type 1 supernovae and type 2 supernovae. Now, what are these? So type 1 supernovae do not show hydrogen absorption lines, such as the Balmer lines, in their spectra. So you can look up hydrogen lines, Balmer lines, and you'll see what that means. then type 2 supernovae do not show the hydrogen absorption lines. So it is really as simple as that. They looked at spectra and they're like, oh my gosh, some of these explosion things have hydrogen lines and some of them don't. So type 1, type 2. Literally imagine a bunch of astronomers dealing with supernova data and looking at the spectra, and some of them have those lines, some of them don't. So they would naturally kind of categorize accordingly, okay? So it turned out that type 2 supernovae are the core collapse supernovae, which we all know and love. Core collapse supernova is probably sort of the supernova that gets talked about the most. So we will see what that is. They have hydrogen absorption lines because the outer layers of a massive star are typically rich in hydrogen. Fusion destroys hydrogen only in the deeper, hotter layers. So hydrogen's absorption line is normal if you have hydrogen in those outer layers, right? So because all that, the hydrogen fusing to say make helium, etc., would be sort of in the deeper layers. Astronomers had difficulty understanding type 1 supernovae until they made a further subdivision into type 1a and type 1b, okay? So what are these two types? So there's type 1a supernova, type 1b supernova. Type 1a supernovae have neither hydrogen lines nor helium lines. So we just mentioned the type 2 supernovae have those hydrogen absorption lines, and they're generally associated with the core collapse supernovae. But type 1 supernovae that do not show the hydrogen absorption lines, let's see what is the deal with them. So type 1a supernovae have neither hydrogen lines nor helium lines. After they decline from their maximum luminosity, so remember that big flux thing happens when this transient event is occurring, and then there is decline in the flux over time. So after they decline from their maximum luminosity, the strongest absorption lines are of iron. How interesting. Type 1b supernovae have strong helium lines and no hydrogen lines. So these are some interesting things that are going on. So one of these things show iron lines, but they don't show hydrogen lines or helium lines. The other one have strong helium lines, but they do not have hydrogen lines. Type 1b supernovae, aside from their lack of hydrogen absorption lines, are very similar to type 2 supernovae. So you will actually see what this means for the type 2 supernovae versus the type 1b supernovae. Now remember, type 2 supernovae had to do with core collapse supernova. So that's a pretty big deal kind of supernova. Core collapse happens for the most massive stars, right? Core collapse will lead to a neutron star or a black hole, pretty much. Thank you for subscribing. Appreciate it. Can we get appreciate it? Please do like, share, and subscribe. And can we get 55 likes and core collapse of the star? That supernova, okay? So type 1b supernovae, you will see that they're kind of similar to the type 2 supernovae. In what way? It is thought that type 1b supernovae are massive stars that completely lost their hydrogen-rich outer layers in a strong stellar wind and then underwent core collapse. So pretty much, we know that the most massive stars will have a core collapse supernova. Like their core is collapsing. The gravitation is so strong. It's such a massive star, it will collapse upon itself when it runs out of nuclear power. Now, we also know, oh, thank you, Joe. Thank you, Joe, for the super chat. We also know that sometimes such stars, when they're undergoing the core collapse supernova and big explosion happens, there could be this stellar wind and whatnot, they can lose their outer layers. So actually, this whole situation of the hydrogen lines not being there is sort of it's sort of a sign of maybe a similar underlying process, but it just lost the outer layer, okay? So that's kind of cool though. It's almost like when it loses the outer layer and we see the next layer, that's kind of interesting. Like it gives you a deeper, literally look into the star or the, you know, of that star that's dying. But even though these are in two different categories, the underlying process could be quite similar, okay? So sometimes the star has lost its outer layer, and so we don't have hydrogen absorption lines, and sometimes it has it, but both are basically undergoing core collapse. So the difference between type 1b and type 2 supernovae is literally superficial. They have the same physics at heart. I love that. A type 1a supernova is completely different. No. So generally, if a star is undergoing a core collapse supernova, it generally means that it's a very massive star, which after death will leave either a neutron star remnant or a black hole. Those are the options, okay? And a lower mass star will leave behind a white dwarf. Cassiopeia. This is the book, guys. Foundations of Astrophysics. It is a book that is used in college. Thank you, Joe, for the super chat. Thank you, Indigo. Thank you, Arnaldo. Hello, Jamar Kasinger. Well, methane is CH4, and it's made of carbon and hydrogen. So carbon does come from stars. Hydrogen comes from the Big Bang. Somebody asked about that. Hello, Trey Brown. Hello, Reagan. Hello, outside. Hello, Benny. Hello, Crybaby. Hello, Ugger. Wayne. Are you Hispanic or Native American? I'm reading. I love that joke. Are you reading a book on? I'm reading a book on anti-gravity. I can't put it down. X power. Oh my goodness, that's too funny. That's too funny. I'm reading a book on anti-gravity. I can't put it down. This is too funny. Hello, outside 365. I am wearing a Spider-Man outfit. There's a cat. One woman in your photo? Which woman? Somebody says, she looks 5'4". I am 5'4". I wanted to be 6 foot tall, but I am just above 5.4. Hello, Dilse. Okay, let's finish up the situation with type 1a supernova. A type 1a supernova is something quite different. They produce around 10 to the 44 joules of energy without detectable hydrogen or helium present and end up as a cloud of hot gaseous iron. So remember, this is the type 1a supernova, which does not produce hydrogen or helium lines for us. Thank you, Taj Dosanj. Hello, Taj. Thank you for the jewels. Hello, Gary. Have you been to the Himalayas? Yes. I have been to the Himachal, Shimla. I've been to Kufri, I think was the town, Kufri. And I mean, of course, I've been to Darjeeling, which is in my same state. I have a new theory on inertia, but it doesn't seem to be gaining momentum. I love these jokes, X-Power. Please do keep them coming. I have a new theory on inertia, but it doesn't seem to be gaining momentum. X-Power, I think I have to promote you. Your jokes are too much. Number one fan right now is Joe. Number 2 is Old Guard. Number 3 is Spearhead. Number 4 is Brady. Hello, Brady. Number 5 is Elijah. Number 6 is X-Power, who has the best jokes. Number 7 is Nokamoi. Hello. Number 8 is Indigo. Hello, my love. Number 9 is Agarwain. Number 10 is Wong. 11, Christ is King. Splitter, Splatter, Greg, Gianese, Zachary. Thank you, guys. Appreciate it. Have you climbed the Everest mountain? Indeed, I have not. I truly appreciate if anybody could with me being a Elijah. Yes. What do you mean, Ababa? Hello, Jaden. Have you been to Punjab? Yes. I have been to Punjab. I think I've been through Punjab. I'm not sure that I've stayed in Punjab. But I did do a bit of traveling in North India, so I believe I've been through it. I want to go to Kathmandu. I think I've been to Kathmandu, but like maybe I was either very little or I maybe did not make it there. I'm not sure. And I've not climbed in Mount Everest, nor do I plan to. I've heard that it's kind of bad for nature to do that. Some of us are paying to learn here. Hello, Elijah. Hi, Rascon. Thank you, Taj. Thank you, Hoover. Okay. So, a type 1a supernova is something completely different. They produce 10 to the 44 joules of energy without detectable hydrogen or helium present and end up as a cloud of hot gaseous iron. To see how a type 1a supernova could be created, consider a white dwarf made of carbon that is just barely below the Chandrasekhar mass. Quiz question for you guys. What is the Chandrasekhar mass? You can look it up. I'm going to tell you in a moment anyways, but additional material from a companion star is then poured onto the white dwarf, kind of like what we saw just now, as the last straw is placed on the camel's back, or less figuratively, as the last hydrogen atom is placed on the white dwarf. Remember, with the pylon happening, the white dwarf is nudged over the Chandrasekhar mass, because remember, it does not have to be stable. A white dwarf does not have to be a stable white dwarf. It's held stable by electron degeneracy pressure. But remember how I said that the lowest mass stars will make a white dwarf when they die, which means that there is a mass associated with this whole thing. If you increase the mass, then you're kind of disturbing the stability of that white dwarf. So sometimes, if it's not too much piling on happening, the white dwarf can take it. But sometimes it's too much, and you've gone past the threshold of the Chandrasekhar limit, which is very important in keeping things a white dwarf. So it ends up being something like 1.4 solar masses. And over time, if you kind of go past this threshold, you no longer have the stability of that situation anymore. Because remember, what is stopping the white dwarf from collapsing further? Electron degeneracy pressure. What is the other thing involved here that we always have involved, right? Which would want to collapse it further? Gravitation. What does gravitation involve? Mass. So if you increase the mass, then you could just tilt the balance that way and get the thing to lose its stability, okay? So that's what's going on here. So this is the last straw on the camel's back, or the last hydrogen atom on that white dwarf. No more piling on. Can it take, okay? So even white dwarfs give up, guys. So if you're in a toxic relationship, you might just consider giving up. So, or less figuratively, as the last hydrogen atom is placed on the white dwarf is nudged over the Chandrasekhar mass. It has reached its limit. Everybody has a limit. So does a white dwarf. And it starts to collapse. Now it's going to collapse because gravitation wins. It's like, dude, this electron degeneracy pressure that was keeping me stable, I'm over the limit now. And what's the other thing going on here? Gravitation. Too much pylon, too much gravitation. I'm going to collapse now into a further compact object by the end of all this, but it might just lead to an explosion in the meantime, right? So that's what's going on here. So as the last straw is placed, whatever, the white dwarf is nudged over the Chandrasekhar limit and it collapses. The density increases until runaway fusion of carbon begins. So just the fact that, because we already know that when you pile on too much onto a white dwarf, you could make helium. Carbon is, a bit heavier, but, depending on how, what the environment is, it might just get hot enough for it to make some carbon, and that's why we might see those lines coming. So basically, it ends up having a fusion into carbon. Think of it as a carbon flash, basically making carbon now. The entire white dwarf, all 1.4 solar mass of it, becomes a fusion bomb. Suppose the initial mass of carbon is, say, 2.8 times 10 to the 30 kilograms. The energy released by fusing it all into carbon, fusing carbon into iron, would be 1.0 times 10 to the 14 joules per kilogram. But this is only 16% as much energy per kilogram as you get by fusing hydrogen into helium, but it's still a substantial energy release. The total energy released by fusing the white dwarf into iron is 2.8 times 10 to the 44 joules. So as soon as you let gravitation win, because now you're not stable anymore, because the white dwarf was sort of this object that is held stable by the electron degeneracy pressure. But if you mess it up too much, now you're letting gravitation win. And in that collapse, there could be more things that are happening. You could make iron, because more extreme because conditions, the more energy, the more heat, the more ability for nuclear reactions to happen and all of that. And then that can have an effect, and that can lead to an explosion and like all this stuff, right? So this is larger than the magnitude of the white dwarf's gravitational potential energy before the collapse. Thus, the entire white dwarf is blown to smithereens, and 1.4 solar mass of iron is mixed into the interstellar medium. So this too can happen. Type 1a supernovae are a major source of iron in our galaxy. They don't produce detectable amounts of elements more massive. So sometimes you're left with this nebula, right? And sometimes these nebulae can be quite metal rich. And who gives us such nebulae? These types of situations, right? Because if we don't have metal rich nebulae, then we wouldn't have us. Hello, Tainted. Yes, so it is gotten more extreme. So that's why it made iron. Because it's not just a simple collapse. As it collapses, there will be further nuclear processes happening, okay? So pretty much the whole thing blown to smithereens and leaving behind, in this case, basically this nebula type of thing probably. So type 1a supernovae are a major source of iron in our galaxy, in our own galaxy. They don't produce detectable amounts of elements more massive than iron. These all come from core collapse supernovae. So all of the elements more massive than iron come from core collapse supernovae, by the way. Tycho's Nova Stella of 1572 turns out to be Nova Stella of 1572 turns out to have been a supernova according to our current scheme of nomenclature. When we turn our telescopes towards Cassiopeia, we see a supernova remnant. So the way to know that a supernova happened sometimes is by seeing that it left behind a remnant. Thank you, El Hogan. Hello, Brawler. Wind down for bed. Hello, B. How are you doing? A brief summary of novae and supernovae. So nova is energy source. It's an event with an energy source which will fuse hydrogen to helium on the surface of a white dwarf. Oh, you sent me a floating heart? And the energy release will be around less than 10 to the 38 joules. Type 1a supernova, the energy source will be something that can fuse carbon, or fuse carbon and oxygen to iron. And the energy will be around 10 to the 44 joules, so more energy released. Type 2 or 1b supernova is going to be, the energy source is going to be gravitational potential energy. It's a core that's collapsing. And the energy release will be 10 to the 46 joules, including neutrinos. So a lot of neutrinos actually escape from such a thing, and a lot of energy is carried away by those neutrinos as well, okay? Hi, Jessie. The photon luminosity is actually slightly greater for type 1a supernovae than for type 2 supernovae. For type 1a supernovae, the maximum luminosity is around 4 times 10 to the 9 solar luminosities in terms of the solar of our sun in the V band. Supernovae are rare events about 1 per century in our galaxy, with type 2 supernovae slightly more common than type 1a. Hello, Nijay. Unfortunately, supernovae within our galaxy are often hidden from us by dust. So there could be some that we miss because there's dust in the way. The most recent naked eye supernova was, of course, the supernova 1987A in the Large Magellanic Cloud. Hello, Dandy Man. I usually only let Neil deGrasse Tyson whisper about nebulas in my ear. So that's a little bit about the events that are called nova, supernova, and such. We covered briefly the nova event, and then we also covered supernova along with the types of supernova, such as type 1, type 2, and then turns out that type 1 has a type 1a as well as a type 1b. And basically, we have talked about core collapse supernova in the past. Those will lead to either neutron stars or black holes, and those are really the most massive stars will lead to such a collapse when they die. And that is very different physics. So the difference is, you keep in mind that the different supernovae have different physics that go on when that thing is happening, when that supernova is happening. A core collapse supernova generally will involve a massive star with a core of iron, and that core gets so heavy that gravitation wins, and also because it runs out of nuclear power. Any kind of slowing in the nuclear reactions or the nuclear reactor and kind of reaching that stable state of having made iron core leads to basically a situation where gravitation can start to win. And if gravitation starts to win in a core, in a very, very massive star, then it leads to this core collapse. So it's mostly gravitational potential energy that is driving the supernova's explosion and explosive energy output, if you will. And we've covered it in the past, and we will probably again next time, that pretty much the core collapse supernova, interesting fact about it is that it also loses a lot of its energy. If I remember correctly, it might even be more energy that's lost as neutrinos as compared to the photons. Okay. When it comes to the stars, we're talking about fusion, nuclear fusion, not fission. Fission is when you break a nucleus. So fission has to do with breaking a nucleus. Like in the atomic bomb. The atomic bomb is nuclear fission. You subscribe to the Big Crunch. Hello, Furry. Hello, Brawler. Hello, Dandy. So nuclear fission has to do with where you cut a nucleus. You can do that with a neutron, actually. So they figured this out during the World War II, I believe, and they did all that stuff. So that has to do with nuclear fission. Fusion is where you make heavier elements or heavier nuclei out of the lighter nuclei, and you fuse together nuclei. And that is also another process, and which would be sort of more in the hydrogen bomb. So the hydrogen bomb is different than the nuclear bomb, okay? Nuclear bomb is nuclear fission, hydrogen bomb is nuclear fusion. And here we're talking about nuclear fusion, which is what happens in stars. Hello, guns. You think you've seen me somewhere? Well, gamma rays can be produced in some, okay, so that's a great question. Gamma rays can be produced in certain transient events called gamma ray bursts. Just wanna make sure it's like, which bomb do you like more? I don't really like any of the bombs, but if I had to pick one, it would probably be the nuclear one. Makes me kind of evil, doesn't it? This is a science channel, yes, physics. We discuss kitty cats and physics, mostly. Astronomy, astrophysics, cosmology. Things like that. Nico is saying, forced smile. Well, maybe I just smile and you don't. What's with the depression? Sorry, that was kind of dark. What is your thoughts on what happens at the end of time? Like heat death or some sort of recursion? She's like, did you go to Waterloo? I don't know what that means. Okay, so I was gonna say, gamma radiation, so light in the gamma ray wavelength. Gamma rays are very energetic photons, right? They're so energetic that at that point you actually would treat the photons as in its particle form. So it's all light. Light has both wave and particle nature. And depending on the wavelength you're looking at, it can either be more wave-like or more particle-like. So on the lower end of the energy, we have something like radio waves or light that is in the radio wavelengths, and those would be more like waves. But then on the higher end of energy, light is more like a particle, and that would be something like a gamma ray. So we do actually see gamma rays sometimes, and these things are called gamma ray bursts. And gamma ray bursts are actually, I have a whole little review book on it on Amazon that you can read. I don't think it's very expensive. It's also on my blog, howtophd.org. But basically, this is one topic of interest to me. I loved it so much that I did like a whole review on it and stuff like that. So, and I have like a little book on it. So basically, gamma ray bursts are also a transient event. They can be anywhere from like under 2 seconds to more than 2 seconds, but typically they're like a much shorter transient event, like 2 seconds or something, right? Whereas supernovae can, this luminosity going up and then the decline over time for a supernova can be, or even a nova, right? A nova like months, supernova days, weeks, months, right? So gamma ray bursts typically are shorter, like 2 seconds, but they can also be longer than that. And they do have an afterglow as well. So long story short, gamma ray bursts are actually associated with hypernovae and mergers. So like neutron star mergers or black hole merger. Those partner things that I was talking about, like though sometimes binary objects, as they're losing gravitational energy constantly orbiting each other, they can eventually collide and merge, and that will also lead to a very big cataclysmic event. And that can cause what we think, that can cause short gamma ray bursts. And then long gamma ray bursts, those are the two types of gamma ray bursts, short and long. Long gamma ray bursts can come from hypernovae, which are the basically supernovae that are even more bigger, like even more big, explosive, intense supernovae. So pretty much to answer the question about gamma radiation, somebody asked, we do see gamma rays. We have discovered gamma rays that are coming from extragalactic sources generally. We do see gamma ray bursts. They're generally extragalactic, and they are generally very far away. And they come from all over. They have an isotropic distribution. Last time I checked anyways. You should confirm all this. And there are two types, long and short. The long ones are associated with hypernovae. The short ones are associated with mergers. Okay? I need to stretch. I never made hot cocoa. Please go to my blog called howtophd.org to learn more about gamma ray bursts. And I have books on Amazon. You can search with my name. I think I'm the only author with my name there. So my name is Oindre, Oindree. And you can search. And I have a review on gamma ray bursts. Which is probably like $1 or something. So it should be quite accessible. It's been very fun, guys. Thank you so much for all your questions, engagement, gifts, chats, comments, conversation. Love it. Love it, love it, and love it. Nice to meet you all. Thank you for being on the live. Thank you for visiting us on this channel and this live. Please do like, share, and subscribe. Thank you for liking the live. Thank you for subscribing. Thank you for telling your neighbors about it and your classmates, your family members, distant sisters, brothers, whoever's. And please do find us again. We go live quite often, especially I think this month I will go live quite often. I used to go live a lot, and then it became a bit more rare. And then now this month there's going to be, I think, a lot of lives as well again. So we also make shorts, clips, videos. So please do show your support there. Really appreciate it. Love to see your comments. Hello, ZTR. You're the bomb. Thank you. Sphincter? What does that mean? So Dr. Who asked about quantum gravity. So we can certainly find some references on that, but I'm not an expert on quantum gravity because indeed I'm not even sure that we have any confirmation of quantum gravity. So, but I can certainly try to find some materials on that topic for you. Thank you for the question. Waterloo. Thank you, Elijah. Hello, Plenty. You should all physics yourself to sleep. Exactly. I think gamma rays are what happened with Hulk, right? I forget the exact details with that fiction topic. Thank you, Dandy. Thank you, Cat Stuffer. I think they're all paperbacks, yes. And Kindle. They should all be on Kindle as well. Gracias, Nijay. AOC, oh my gosh. Thank you, my darling. Well, AOC is in politics and I'm in physics, but I think we're the same. Ah. Thank you, guys. Thank you. Yeah, they have a wall tree. You are dismissed, yes. Class dismissed for now, but be here on time next time. I'm in Boston. You guys are funny. You're very funny indeed. Hi, Taj. Yeah, it's 1:49. Boston sounds not too fair? What do you mean? I'm on Instagram. You can find my Instagram in the description. And follow. Follow. Follow on Instagram, Facebook, TikTok. And also, those other platforms, I have some physics on there, but also it's more like travel and other lifestyle stuff. The physics is mostly here, and the cats are mostly here. Hello, Leon. Are you in Ivy League? No. Do I have a booger on my nose? Well, don't we all? Hello, Randy. Hello, Daniel Priestley. Favorite Indian dish? Rice, dal, fries. In Bengali, we say dal bhat, aloo bhaja. That's my favorite. I enjoy these little lessons. Thank you. How are you doing, Snowcole? How are you? Like and sub. Are you from Pakistan? Are you a teacher? Looks that way, doesn't it? Australia. Hello. Hello, Gazor. I will be soon. How are you? Australia, what time is it? Hello, Herbs. So I am from India, but I am like half from my mom is like, speaking of Pakistan, I do have a Pakistan connection. My mom's family is all from current Bangladesh and back then East Pakistan. So Pakistan is also from India. So yes, sure, I can be from Pakistan. Hello, Kanye. Hello, Troy. Hello, ZTR. Hello, Sunna. Hello. 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 Can you guys do a gift? Can you do a super chat to say good night? Good night. That would make my day. Oh, thank you, Cassio. Talk a little about emission of radiation of black holes and its loss of mass. Mr. Salty. Thank you. Spearhead. Spearhead is saying good night. Good night and sleep tight. Hello, Roland Dietz. Touch. Hello, KJ Kiale. Hello, Troy. Hello, Ugger. Oh, thank you so much, Ugger. Ugger Wayne Blade is doing a super chat. Thank you so much. Ugger Wayne Blade 2644. Thank you for the $2. Acacio, thank you. Acacio has done a super chat. Thank you so much. Thank you guys so much. You should rewind, by the way, to see the full episode if you're just now joining. Spirit, thank you. 6 p.m. in Australia. I liked last live and a bit intimidated by your knowledge and natural beauty. Gazor, thank you for putting into words those kind thoughts. Thank you, my lovely people. Hello, Stealth. Thank you, Troy. Thank you, Agar. Mr. Salty. Thank you. Good night. I don't think I've been to Colorado Springs. I really want to, though. Hello, Chad. Hello, Steve. You know what I realized? I still have to shower. I did not shower yet today. Today is a weird day because I did not go to the gym today, but I did take a walk earlier. I went to the bakery and I walked there and I walked back. And it's so cold. Yeah, yesterday. Hopefully today I will go to the gym because then I can shower at the gym and I will be on a schedule that I like. Yeah, I have to shower and go to bed now. Hello, Quincy. Thank you. If a girl says she's married, does that always mean she's uninterested? Well, she's kind of already in a relationship, but she's just letting you know that she's married. I think I would just take the information at face value. You could ask her, hey, I know you're married, but do you want another relationship? Just say it like that. The super chat says 18.94. Can we have it go above 20 just so that the number is nice? As an agony aunt, I should be making way more than that. This is physics plus psychology. I'm in Boston. Tell her save your name under dominance. Could you please like the live? Can we get 75 likes? And rewind the live as well. rewind. Hi,